Let me introduce myself. I am Dr. D.K. Pratihar, Professor of Mechanical Engineering Department, IIT Kharagpur. I am going to teach the course on traditional and non-traditional optimization tools. I welcome you all to this course. Now, for this course, the textbook which I am going to follow is this Soft Computing Fundamentals and Applications, written by D.K. Pratihar. Now, let me start with the first topic, that is principle of optimization. Now, before I start learning this particular course on optimization, several questions may come to our mind. These are as follows: what is optimization? That is, what do you mean by an optimization? Why do you need optimization? The next is how to represent an optimization problem in the mathematical form. How do we classify the different optimization problems? How does an optimization tool work while determining the optimal solutions, and so on. Now, I will try to answer all these questions one after another. Let me start with the definition of the term optimization, that is, what do you mean by optimization? Optimization is the process of finding the best solution out of all the feasible ones. Now, let me take one very simple example. While delivering the lecture, nowadays we use laser pointer, but previously we used to use some sort of wooden pointer. Now, if you see the wooden pointer, the designs of wooden pointer, now this wooden pointer is nothing but the conical shape pointer. It looks like this. It is something like this. Now, this end is nothing but the gripping end, and this is the pointing end. Supposing that on a bin or a bucket, so we have got several designs available of this wooden pointer, and now I will have to find out the best one. Now, this is nothing but a task of optimization. Now, the next is, why do you need this optimization? We need the principle of optimization because to be in competition in dynamic and competitive market, we will have to produce goods which are cost effective and efficient. Now, the principle of optimization is going to help us to ensure the cost effective and efficient product. Now, mathematically, if you want to represent what do you mean by optimization, now I will have to take one example, that is y equals to f x y equals to f x. So, this is a function of only one variable. Now, what we do is we try to find out the first derivative, that is f prime x, and we put equals to 0. Now, we solve for x, supposing that we are getting x equals to x star. Now, at x equals to x star, there could be either optimum solution or there could be inflection point. Now, this optimum solution means it could be either the maximum or the minimum. Now, by inflection point we mean this is neither a maximum nor a minimum. Now, if you want to investigate further, we try to find out the higher order derivative, and supposing that n represents the first non-zero, the higher order derivative. Now, what we do is we find out the higher order derivative. Now, if this particular n, which is nothing but the first non-zero higher order derivative, if it is found to be odd, then x star is nothing but an inflection point. On the other hand, if n is found to be an even number, there could be two sub cases. If the value of the derivative is seen to be positive, then x star is a local minimum point, and if the value of the derivative is found to be negative, then x star is a local maximum point. Now, let me try to explain this with the help of one numerical example. Now, the problem is as follows, like we will have to find out the maximum or the minimum or the inflection point of the function f x equals to x cube. Now, what we do is we try to find out the derivative of this particular function. We try to find out the derivative of this particular function, that is your f prime x, and that is nothing but 3 x square, that is nothing but 3 x square, and we put this equals to 0, we solve for x, and supposing that we are getting x star equals to 0. Now, we try to find out the higher order the derivative. So, f double prime x is equals to 6 x. Now, if I put x equals to 0, this will become equal to 0. So, this is not the non-zero quantity. Next, we go for the third order derivative, that is f triple prime x, and that is equals to 6, and it is not equals to 0. That means, the value of small n, that is equals to 3, and it is an odd number. Now, as n is an odd number, so this indicates that x star equals to 0 is an inflection point. Now, if you see the function plot, y is a function of x. So, this shows actually the function plot, and here you will find that at x equals to 0, this is neither a maximum nor a minimum, and this is nothing but a saddle point on or an inflection point. Now, the next question is, how can we represent an optimization problem mathematically? Now, to represent the optimization problem mathematically, what you will have to do is, so I will have to take one example, and let me try to take the example of the wooden pointer. That means, we will have to find out the optimal design of the wooden pointer, and to find out the optimal solution, how to represent mathematically, that I am going to discuss. So, this is the schematic of one wooden pointer having conical shape. Now, this is nothing but your the d is nothing but, that is the diameter of the gripping end, and L is the length of this particular the wooden pointer, and this is actually the pointing end. Now, what we do is we try to find out the optimal design based on the condition that it should be light in weight, so that we can handle it very easily, and at the same time there should not be any mechanical breakage, and the deflection of the pointing end should be as minimum as possible. Now, here this diameter of the gripping end and the length of this particular the pointer. So, these are nothing but the design or the decision variables, and rho is nothing but the density, that is the pre-assigned parameter, and that is a fixed quantity. Now, using this, so what we can do is we can find out the mathematical formulation of this particular the problem. Now, what we do is we try to find out the volume of this conical shape wooden pointer, and the volume is nothing but your that V is nothing but 1/3 pi d by 2 square multiplied by L, and mass is nothing but is the rho is the density multiplied by the volume, and very easily we can find out this particular the expression. And once you have got this particular expression, so I can find out. So, this is actually the mass of this wooden pointer, and it is subjected to two conditions: the deflection of the pointing end, it should be less than equal to the allowable deflection, and the strength should be greater than equal to the S minimum required. Now, these are nothing but the functional or the behavior constants, and the objective function is nothing but to minimize the mass, and of course, this will be subjected to some geometric or the side constant or the variable bounds. Now, here you can see that this d is lying between d minimum and d maximum, and L is lying between L minimum and L maximum. These are nothing but the variable bounds or the geometric constants. Now, here in this mathematical formulation, so minimize mass is nothing but the objective function subjected to two conditions, those are nothing but the functional or the behavior constants, and the variables are having some range d and L, those are nothing but the geometric or the side constants. Now, for any optimization problem, the first thing you will have to do is you will have to identify the design variables. So, mathematically you will have to express the objective function, and you will have to find out the functional or the behavior constants if any, and of course, there should be some variable bounds. Now, the presence of this functional constant or the behavior constant is not must for all the optimization problem, but the geometric constant and or the side constant are to be there for all the optimization problems. So, this is the way actually mathematically we can express the optimization problem. Now, the next is how to classify the different optimization problems. Now, optimization problems have been classified in different ways. For example, the first one is depending on the nature of the equation involved. So, depending on the nature of the equations involved, the optimization problem could be classified into two groups. Now, one is called the linear optimization problem, another is called the nonlinear optimization problem. Now, by linear optimization problem, we mean that both the objective function as well as the functional constant should be the linear function of the design variables. For example, here, so our aim is to maximize y is a function of x 1 and x 2, that is nothing but 2 x 1 plus x 2. So, this is actually the objective function, this is actually the objective function, and it is subjected to two conditions: x 1 plus x 2 is less than equals to 3, 5 x 1 plus 2 x 2 is less than equals to 10. So, these two are nothing but the functional constant, and of course, there should be variable bounds x 1 comma x 2 is greater than equals to 0. So, this is nothing but the side constant, and here both the objective function as well as the functional constants are linear function of the design variables. So, this is a linear optimization problem. Now, the next is nonlinear optimization problem. Now, for this nonlinear optimization problem, either the objective function or any one of the functional constants or both will be nonlinear function of the design variables. Then it is called the nonlinear optimization problem. Now, the second classification is based on the presence of the functional constants. Now, as I told that the presence of functional constant is not a must, Now, for the optimization problem, if there is no such functional constraint, that is called unconstrained optimization problem, and if there is at least one functional constraint, that is called the constrained optimization problem. And it is very important that this site constraint or the geometric bound has to be there for all the optimization problem, otherwise it cannot be defined. Now, the third classification is based on the nature of the design variables. Now, based on the nature of the design variables, optimization problem can be classified into three groups. The first one is the linear programming problem, where all the design variables or the decision variables are integer. That means, the whole number like 10, 11, 12 like this. Now, for the real valued programming problem, the design variables are to be fraction or the real number like 10.5, 12.6 and so on. Now, the third type, that is called the mixed integer programming problem. Here some of the variables will be integer and the other variables will be real. So, this is a combination. The next classification is either it is static optimization problem or dynamic optimization problem. Now, let us try to explain what do you mean by the static optimization problem. Now, let me take one very simple example. Now, this example is supposing that I have got one cantilever beam and here there is one concentrated load acting, that is P, and this beam is having the length L and cross section having the dimensions A and B, and here the cross section has been kept constant throughout the length. Now, what is our aim? Our aim is to design one optimal cantilever beam, so that there should not be any mechanical breakage during its working, and our aim is to find out a beam which is having the minimum weight. Now, if this is the optimization problem, so I can formulate as an optimization problem mathematically, and here A and B does not depend on L and they are not varying with L. So, this type of optimization problem is known as the static optimization problem. Now, the next is the dynamic optimization problem. Now, here I am taking the same example of the cantilever beam, but here this particular cross section is varying along this length of the beam. A and B are varying with L, that is the length of the beam. That means, your cross section is not kept fixed along the length, and this type of optimization problem is known as the dynamic optimization problem. Here some of the variables, design variables, are dependent on some other design variables, and this type of optimization problem is known as the dynamic optimization problem. Now, this is how to classify the optimization problems. Now, I am going to discuss how does an optimization tool work. So, what is the working principle of this particular the optimization tool? Now, to explain this, let me try to take the example of a constraint optimization problem. That means, there will be objective function, that is y is a function of two variables x 1 and x 2. That is this particular mathematical expression I am just going to consider for the objective function, subject to the condition the g I x 1 x 2 is less than equals to c I, her I is 1 to up to n. So, this is nothing but the functional constant, and there are n number of functional constants, and x 1 is greater than equals to x 1 minimum and x 2 is greater than equals to x 2 minimum. So, these two are the variable bounds. So, this is nothing but a constraint optimization problem. Now, let us see how to solve this particular the constraint optimization problem. Now, to solve this constraint optimization problem, what we do is we try to make a plot of the design variables like x 1 and x 2, and here actually what we do is first we try to plot the side constraint. The first side constraint was x 1 is greater than equals to x 1 minimum. So, this is actually the side constraint, and the left side is infeasible, right side is the feasible one. The second side constraint was x 2 should be greater than equals to x 2 minimum. So, bottom is infeasible, top is feasible. So, I am getting the feasible zone like this. Now, I am just going to draw the functional constraint. Supposing that this is the first functional constraint. So, this side is the infeasible and this side is the feasible one. Might be the second functional constraint is this. So, this side is infeasible, other side is feasible. The third functional constraint is something like this. So, this side is infeasible, this side is feasible, and the fourth functional constraint is this side is infeasible and this side is feasible. So, I am getting one feasible zone, it is something like this. So, this is nothing but the feasible zone for this particular your optimization problem. Now, any point which are lying inside the feasible zone are known as the free points, and the points which are lying on the boundary of this particular feasible zone are known as the bound points. Now, optimal solution could be either the free points lying inside the feasible zone or the bound points which are lying on the boundary of the feasible zone. Now, how to find out the optimal solution? How does an optimization algorithm tries to locate the optimal solution? So, what we do is, so we have got this objective function, that is your this y is f of x 1 x 2. So, that is nothing but x 1 minus a square plus x 2 minus b square, and this is a minimization problem. Now, all of us we know that the minimum value of this particular function is nothing but 0, because this is the sum of two squares, and corresponding to the solution 0, the value of x 1 will be equal to 1 and value of x 2 will be equal to b. Now, so if I consider a particular value for this particular y, that is say 0, now what you can do is, so corresponding to this y equals to 0, so I can draw one circle, and that will be nothing but this point circle. So, that will be the point circle. Now, similarly what you can do is, we can take some other value for this particular y, say y 1. So, corresponding to this y 1, so I will be getting one circle here. Corresponding to y 2, I will be getting another circle here. Similarly, for y 3 another circle, y 4 another circle, y 5 another circle we will be getting, and this is nothing but the contour plots for this particular the objective function. Now, the moment I consider y equals to 0, that means I am here. So, this particular point is actually the optimal solution if I consider the unconstrained optimization problem. That means, there is no such functional constraint. The moment we consider the functional constraint, this will not remain as the optimal solution, because this is lying in the infeasible zone. So, what we will have to do is, we will have to consider the next higher value for this y, say y 1. Now, if I consider y 1, still this particular circle is there within the infeasible zone. If I take y 2, that corresponds to a circle which is also lying in the infeasible zone, but if I consider y equals to y 3, so that particular circle is going to touch the feasible zone at this particular point. That is why, so this particular point is called the optimal solution for the constrained optimization problem. However, for the unconstrained optimization problem, this is the optimal solution. That means, if I put some constraints in terms of quality, so I will have to quality of the solution in terms of the objective function value. And let me repeat once again, for the unconstrained optimization problem, so this is the optimal solution, and for the constrained optimization problem, so this is the optimal solution. So, this is the way actually one optimization tool works, and for any optimization tool actually what we will have to do is we will have to find out the search direction and we will have to find out the step length for each of the iterations. Now, the way one optimization tool determine the search direction and the step length, that way actually varies from tool to tool, techniques to techniques, and that is why we have got a large number of traditional tools for optimization.